Yeah. So I'll give a quick introduction for you.
Okay.
So, hello everyone. We have Professor Cliff Burgess today with us, and he's a professor at McMaster University and Perimeter Institute. So he specializes in cosmology, string theory. He has a very beautiful and one of my favorite books on effective field theory. So please check that out. And we're very glad and lucky to have him here. So over to you, Cliff.
Thank you very much. Thank you for the invitation and the kind introduction. It's always still amazing to me at my age that we can have talks all over the world like this, and it's be nice to be there, but it's nice to have the opportunity to speak to you all. So I'm going to share my screen now. I want to make sure that this kind of goes through the way it's supposed to. So I think you see now. You can. I think it looks like you can see the title screen, but you probably can't see my mouse, it looks like. So I should say in words. Um, okay. Okay, good. So my understanding is that, so you've all had this great course on or school on general relativity, and my goal is to kind of pitch the picture of we live in this really odd times where general relativity works fantastically well, and yet everybody's trying to modify it. And so, why? You might think that, we've got a good theory. Why are we not going to not be happy with it? So I want to kind of go through the the both the evidence, why we like general relativity so much, why it's the evidence for it is so overwhelming, but also the reasons that people are motivating people to change it, and along the way, the main message is there's this picture of how there's a famous set of problems with general relativity and how you incorporate quantum corrections to them. And and the way that was thought about back in the 60s by Feynman and Dirac and others was that it seemed a disaster that nobody knew how to do anything. And that really meant that you had to have a split brain where half your brain knows about quantum mechanics and the other half knows about gravity and they don't talk to each other. But the modern picture is better than that, that there's really if you think about quantum effects on large scales where we measure things, that's actually a solved problem, how to do that with gravity. Whereas quantum effects for short distances, which we don't yet have access to experimentally, that's where the deep issues are that people are probing in quantum gravity. But the fact that that's not yet completely understood is not limiting the accuracy with which we can make predictions at low energies where we need to in order to compare it with observations. And so the main message of the talk is going to be that effective framework as to why people want to modify gravity, um, why we understand gravity in a quantum mechanical way, and why that understanding, how it helps sort the various proposals of modifying gravity for plausibility, that some of them are crazier than others. And so it's useful to have that as a benchmark, as kind of where the talk goes. But I should also say before I start that, so what'll happen is that I'm going to rank various theories, and if you're working on one of the theories gets ranked lowly in this ranking, I wouldn't stop working on it. There's this old joke in about the linguistics professor, who tells the class that there's no such some languages a double negative means a positive, and some languages a double negative means a negative. But then he asserts, in no language does a double positive mean a negative. And there's a pause, and then the student says, "Yeah, right." And so that kind of illustrates that whenever you're told from on high that this is the way things are going to go, you should always be skeptical. But it's also useful to know how these rankings go, and hopefully what you'll get from this talk is the things that need to be done to convince other people about why that direction is actually better motivated than I'm going to sell here. So it's very much going to be the take that comes to you from the effective field theory way of thinking about gravity. So let's get started. So see if I make sure I can advance my slides. There you go. That's changed, right? Good. So there's four parts. I want to first, you know, the king is dead. Long live the king. I want to first start off with why we like general relativity so much, and then the second section will be what are the reasons that people, broad brushstroke reasons why people are trying to modify it, which will include this quantum problem, but it's one of many of the motivations. The third part is the main part, and that'll be where I'll be summarizing the modern picture of how quantum effects and gravity interface with one another. And then the last part will be the scorecard part. And probably I'll be short of time at that point, so it'll be very brief. So I'm not going to actually go through specific models of modified gravity separately, but I'll kind of mention them. And if you want to hear more about any of them, please ask. Also, during this talk, interrupt me if you have questions. I know online it's very difficult to get a sense as to whether people are following, and silence tends to make me think that I'm boring people and I'll talk faster. So please do interrupt if you have questions. And I don't know if the moderator can watch I don't have the chat window in front of me, but
Sure, I'll do it. No
that'd
worries.
be great. Yeah, thanks. Okay, so let's start off with the evidence for general relativity, which is amazing evidence. And just to kind of get us all on the same page, I know you guys are experts at this now because you've seen it, but just to kind of in the nutshell version of general relativity. Once special relativity happened, everybody knew that Newton's gravity had to change, and it had to change because of the problem with signals can't go faster than light, and you can't have action at a distance where things move instantaneously. I remember when learning about this as a student, people had to. The lesson of relativity was people had to think in terms of fields, and I remember thinking, well, fields seemed like a very redundant concept because we were told if you have the Coulomb force, we had a rule for getting forces. You tell me what the charges are and where they're located. And I had a rule to figure out what the forces were. And then the field way of thinking about it just seemed like it added a new layer. Now you tell me where the charges are. I tell you what the fields are. And then given the fields, I figure out the forces. What did the field do for me? It just seemed like it was a waste of time. And of course, the issue there is as long as when you're learning these things, you tend to be doing static problems. It's as soon as your sources are moving that you really see the utility of a field. So if you have something like in this picture where a charge is there and there's force lines radiating out or field lines radiating out, say that's a charge or something, then you move it, and what happens is everywhere in the universe they don't see that you've moved, and so they're still feeling that they're attracted or repelled by where you were until this wave moves out through the field and brings the news to them that you've moved. And that's kind of what the field's doing for you. It's showing you that things don't happen instantaneously, and that's what's required to reconcile with relativity of simultaneity and special relativity. So electromagnetism kind of did that for free because that's kind of how Einstein figured out what the rules were that we were supposed to be using in relativity. But gravity clearly didn't, and so something had to change. And the question is, what was the field that they were going to use for gravity? And there's this famous narrative about the principal equivalence that sets up what the field is, and actually it's often misinterpreted. So I'm taking you through something I think you know already, but I want to emphasize something. So there's a story that you know that if you're in a constant gravitational field and you drop two apples and they do something, and it's indistinguishable from what you would have seen if you're in an elevator without a gravitational field, and the elevator is accelerating. And so people come away with that often with the statement that, or the sorry, let me turn the sound off here. The people can mistakenly come away with that with the statement that there's nothing physical in gravity. And that's the wrong takeaway, I think. Really, the way to think about this is that if you really were over the Earth and you were a very careful experimenter, you would know you were over the Earth in that elevator because the force wouldn't be constant. It would be pointing towards the center of the Earth. So by looking at the differences of the gravitational force in that elevator, you could distinguish a gravitational field from an accelerating elevator. And that's the important thing, is that it's these differences of forces, which are what we call tidal forces. That's the thing that needs a field description. And in general relativity, that's the curvature. So we talk about the geometry of space as being what relativity is describing, but flat space also has a geometry. The thing that is gravity is the curvature of space. And that's, as you know from your course, um, curvature is what gives you tidal forces. It gives you the relative change of forces between different positions. So now, that course took 10 years to figure out. And but now in 1916, he tells us what the the theories of curvature. And I want to just summarize here a couple things that I think you've seen in your courses, but that I'm going to use just so that it's concrete. So you know, of course, that the geometry is characterized by some metric, g mu nu, and then you know that there's a Christoffel symbol that you build from it, which has got one derivative of the metric is all I really need you to know about that, and then some nonlinear function of the metric. And then the curvature involves the derivative of that Christoffel symbol or the square of the Christoffel symbol. So everything in it involves exactly two derivatives of the metric, either one derivative squared or a second derivative of the metric. And then the action that Einstein uses is this Einstein-Hilbert action, which is proportional to the scalar curvature. And the proportionality constant is, I'm calling m Planck squared. I'm using units where h bar and c are 1. Uh, and what you do with this action depends on who you are. If you're a classical person, then you vary the action and you get the classical field equations, and that's what you've been doing in this school for some great detail. And so the variation of that Einstein-Hilbert action gives you the Einstein equations. But if you're a quantum mechanics person, then what you're doing is you're taking that action and you're sticking it in a path integral the way you would have done for any other action. And you're imagining that the field that you're integrating over is the metric, but you're really thinking that it's in a semi-classical limit, some big classical metric, and then it's fluctuations around a classical metric that are the quantum things that you're integrating. And all I need you to know, what I want you to remember later on in the talk is that the action involves exactly two derivatives, the Einstein-Hilbert action. And that's going to be important because in the describing quantum effects, we're going to be counting the derivatives because ultimately the classical expansion in gravity is really a low energy derivative expansion. And so the numbers of derivatives in interactions are important. All right, so now back to the story of tests. And so immediately right off the shelf, there were the three classical tests of general relativity. There was the precession of the orbit of Mercury that wasn't accounted for by the fact that the sun's not an exact sphere. And that was solved in a pre-existing anomaly. Then there's the bending of light of the sun. So there's you look at some stars when the sun's not there, and then you look at them when the sun's in the foreground, and the only way you really, in those cases, could see them was if you had an eclipse or something to make the sun not too bright. But the important part was that the stars move apart from one another when the sun's in the foreground, and that's because the light from the star is being bent as it goes around the sun by the gravitational field of the sun. And so the measurement of that was a significant thing. That happens also for Newton, but there's a factor of two difference in the prediction, and so it wasn't clear that the errors at that time were good enough to see that factor of two, but it was sociologically convincing at the time, those experiments. And then there's the other third thing was the classical redshift, the energy particles, including photons, climbing out of a gravitational potential well will have to lose energy, and so for photons that means that they lose they redshift. And there's nothing exotic about photons in that sense. Everybody's losing energy. The only thing that's different between photons and ordinary particles is that for photons, when they lose their energy, they don't slow down. That's the counterintuitive part. But so these are the things that they knew they were getting right, basically from the get-go. But now that's just such a small piece of the evidence. The lensing story where light is bending as it goes around sources is something which in cosmology that's all over the place. You look at clusters of galaxies like this one, there's galaxies in the background, and the light from them is being bent by the mass of the galaxies in the foreground. And so these blue arcs in this picture are multiple images of one thing, a galaxy in the background. And you can kind of tell that because the length of the time it takes to travel on these different trajectories, it takes light to travel, can be different. And so what will happen is that, say, there's a glitch or something in the spectrum or in the amount of light appearing on one of these images. A little bit later, that same glitch arises, but it's not simultaneous because the time taken to get here by the light, depends on the path it took. So there's lots of evidence of lensing. This is called strong lensing, but there's also weak lensing where the bending of the light isn't so strong that you actually see multiple images, but it does distort images a little bit. And by measuring this distortion of the shapes of galaxies in a field of view, you can turn this bending of light into a measurement of how much mass was in your field of view. And so there's lots, these things are no longer exotic, they're just tools that people use to describe gravity. The whole relativistic astrophysics story of black holes and neutron stars and pulsars, of course, wouldn't have been understandable without relativity. You had to have a way of understanding relativistic gravity. We're going to come back to pulsars, but the neutron stars are just these stars that are where gravitational force is being balanced by the degeneracy pressure of neutrons. So it's like a neutron, it's like a nucleus, but where the size of the nucleus is a city, kilometers across. And of course, they have exotic gravitational fields. They have large magnetic fields, and as if they often are spinning, and that's where pulsars are. The pulsars are we interpret them as being neutron stars that are spinning, and I'll be saying more about pulsars later on. Is kind of why I'm mentioning that. The whole story of relativistic jets and black holes, black holes can convert something like more than 10% of the energy of things that's falling in, the rest mass of things that's falling in into energy that can be often emitted as a jet of material. And you compare that to nuclear reactions, where you're only getting about 1% of the stuff out of the rest mass of the nuclei out of the reactions. It's just that gravitational relativistic effects are much more efficient at converting energy than other things that we know about. And so the fact that you see these enormous energy sources, it'd be hard to understand them at all if you didn't have access to relativistic gravity. The cosmology, the whole beautiful story of the microwave background, which is what the picture is showing you, and where you're looking at the light in the early universe was bouncing around in a gas of hydrogen, and at some point it cooled down to the point where neutral atoms formed in this gas, and at that point the universe becomes transparent, and the light that was bouncing around is still there, and it's been seen. And you measure these maps of the sky, uh, and what you're measuring is the temperature of that hydrogen as a function of the direction you're looking. And so the distance between the hot and the cold places, that's basically sound waves and hydrogen. We know a lot about what's going on there. It's like someone's given us a ruler at the other end of the universe where we know the distances between things, and we can also measure the angles between them, and so learn a lot about the geometry of the universe from that. The general relativity has been tested in great detail in the solar system. And here I'm putting in some numbers to get a sense as to quantitatively how good these tests are. The best tests often come from the Cassini space probe, which you remember was orbiting Saturn. And what people do is they parameterize the geometry of the solar system in a general spherically symmetric way. And then they have this is the specific metric, the Schwarzschild metric that Einstein predicts is just one of the metrics you could have been looking at in that parameterization. And they have parameters alpha, beta, and gamma that measure the classes of metrics, and they're normally chosen such that when alpha and beta and gamma are one, that's the metric, the Schwarzschild metric that relativity predicts. And then you can quantify by measuring how things move in this general metric, and thereby measuring what alpha, beta, and gamma are. You can quantify how well general relativity is doing. And so what people do with the Cassini probe is they send signals back and forth to the probe from the Earth, and the time it takes those signals to make the round trip depends on whether or not the sun is in between us. If Saturn's on the other side of the sun or not, that'll change how long it takes the light to make the trip. Apart from just the geometrical length, in addition to that, there's an effect which depends on whether or not the light moves through the gravitational field near the sun. And the fact that the agreement of what's measured in that delay, what's called the Shapiro time delay, the agreement with that with general relativity puts a constraint on gamma in particular, which is that you can see is that at the 1 part in 10 to the 5 level. So we're talking very precision measurements that are being done that test the accuracy of gravity. And I want to emphasize that because when you compare to measurements that are that accurate, part of your story has to be how big your theoretical error is when you make your predictions. And one of the uncertainties in making these predictions is how big are quantum effects. And so if someone sells you a theory of gravity where they can't tell you how big quantum effects are, it's kind of silly to compare it to observations, because if you don't know how to include quantum effects, what that really says is you have an uncontrolled theoretical error, so you don't really know what your accuracy of your predictions are. And this gives you an idea about how good the prediction has to be, how good the accuracy has to be. It has to be at least a part in 10 to the 5 in the solar system. Another test is spectacular test that's been around for decades now is the binary pulsars. So you have a neutron star which is orbiting, and the beam that it's emitting, because it's rotating, sweeps around the sky, and it passes by us, and it looks like it's a rapidly repeating signal, but it's very stable, and so it's like a clock that somebody's put in a gravitational field. This particular neutron star is orbiting another star, and you can measure all the orbital properties by looking at the Doppler shift and very accurately measuring the timing of the arrival of these signals. And one of the things that that shows is that the orbit this pulsar is decaying, so its period is changing. There's a non-zero d period d time for this orbit, and that's interpreted to be due to the energy loss into gravitational waves. That this any orbiting accelerating thing is going to be emitting waves, just like in electromagnetism, and in gravity that's true too. And so there's a comparison. They've been watching this pulsar since the 70s, this particular, the Hulse-Taylor pulsar, and the comparison of the plot shows you the uh, the it's called the periastron time. Periastron is just the point of closest approach of the orbit. It's like perihelion, but astron for star rather than the Earth. Um, and so the timing between successive periastrons is the period of the orbit, and you're watching on that plot how it's getting smaller and smaller with time. And the curve that it's being compared to, the errors in that plot are kind of small enough that you don't really see them in the plot. And the curve that's being compared to is the prediction of general relativity, and that's very impressive. And when you see that, you're normally inclined to think, "Oh, that was a very nice fit." But this curve is not a fit. This is what they've done is they had the thing that's not known classically is the mass of these two objects. And what they do is they determine that using agreement with other predictions of relativity. And then given those masses, there's just an absolute prediction of what general relativity would give you. And this is what it is. And so it's not being fit to the decay of the orbit. It's just being fit to something else. And then it just has to agree with the decay of the orbit if general relativity is what's going on. And you see it's a very impressive agreement with what's going on. So again, super accurate over a long period of time. The way that they get these masses is what you're seeing here now is there's more than one binary pulsar that's known now, and the things that's not known are the masses of the pulsar that you see and also the mass of the thing that is orbiting. And these various plots here are showing you are various relativistic effects that, like the precession of the orbit, in the same way that Mercury's orbit is precessing around the sun because of relativity, the orbit of the pulsar around its companion is also precessing due to relativity. And so that's one of the things you can measure. That's the omega dot line that you can kind of see. And top left square is the same pulsar as in the previous slide. And so the diagonal green dotted line is the what you would expect for the precession of the orbit as a function of the masses of the two things in the orbit for general relativity. And there's actually two lines there. You can't quite see it, but they're separated by uh, there's two lines that are showing you the range of values that are consistent with the prediction under the range of uncertainties of the masses that people would have had. And these other things like P dot is the P dot, the red curve is that's the thing I was showing on the last slide. I was showing you the rate with which the period of the orbit decays. And then the gamma is a measurement of the relativistic time dilation that's happening because things are moving. And so that dashed green line is the measurement of that particular relativistic effect as a function. That's the prediction as a function of the two masses. And then the thing measured R and S, those are like, for example, there's two horizontal dashed dotted lines in the upper left panel. There you can now see the distance between the upper and the lower ones are just the range. They set the range of what this variable R would have been. For these two stars, and they show that there's a fairly large uncertainty in the masses, and so in general relativity, given the uncertainty we have on the masses of those stars, you have to live between those two lines for the variable R. What R and S are, it's just the same Shapiro time delay that I mentioned for the Cassini probe. But there's actually two variables in this case because in the Cassini probe case, we were always in the plane of the orbit of Saturn because all the planets were orbiting in the same plane. But in a binary pulsar, there's an issue of the angle of inclination of the orbit to us, our line of sight. And so that introduces two variables that you can measure rather than just the one. And so those are called S and R. And the main message is in the top left plot is that those predictions are all predictions from general relativity. And if they're all true, if general relativity is true, they all have to agree. There have to be a choice of M1 and M2 for which they all agree with the observations. And so That's the important thing. And what happens is that all these curves, you notice that they all intersect. And so there's a place where say the p dot curve is tangent to the omega dot curve, and that's inside the band that's allowed for the R curve. And all of these separate ways of testing general relativity, they're all consistent with one another for some choice of M1 and M2, and that's how they determine what M1 and M2 are. And in this particular case, you could have not had the p dot curve, and you could have used all the other things to figure out what the masses are. And that's what they did in the plot in the previous slide, is that they got the masses by the coexistence of these parameters. The same thing, and these other slides it's the same logic. Essentially, in these other slides, they haven't been watched for so long, so the errors are bigger, but it's the same kind of thing that if you believe that general relativity is working, then all of these measurements of these various quantities have to agree for some choice of the masses. And in the bottom right case, it's kind of there's more curves than normal, and that's because that's an example where they've got a pulsar orbiting another pulsar, and so you can see them both, and so because of that, there's more things you can test, and so there's more curves there. And again, it's phenomenal that the errors are quite small because they've been watching for many years, and they're always consistent. And so it's the consistency of these multiple redundant lines of evidence that make you really think that this is a good test of general relativity, and it's also telling you the masses of these things. So that's a fantastically accurate. I'm laboring that because it emphasizes the accuracy. It's not just a qualitative agreement. It really is an accurate agreement with what we see in the sky. In modern times, there's now tests of general gravitational waves, starting about 10 years ago. And that's a whole new direction in which we can now test general relativity. And now we can do it in places where things are more relativistic, such as when black holes are merging, as opposed to non-relativistic systems like the solar system. And there's lots of tabletop tests or satellite tests of forces, testing basically whether or not the force of attraction of things is going like the inverse square law as a function of separation, or testing that that the source of gravity is really the total energy in the object as opposed to some chemical composition dependence. And the plots here are showing you if you were to add another force to gravity and it'll have a strength and a range. And if you allow those things to be chemical composition dependent, then you can constrain agreement with the observations constrains how strongly these forces can be coupled. And so the plot on the bottom, the left-hand plot, the thing on the left is basically the strength of the force relative to gravity. And gravity is already the weakest force we know. And you can kind of see that the yellow areas are excluded by observations. And so for some of them, the observations go right down to 10 to the minus 10. And this is actually an old plot. Those same observations now go down to 10 to the minus 15 to the tests of the equivalence principle. We're already constraining the existence of forces that are competing with gravity at a part in 10 to the 15 compared to the strength of gravity, which is already fantastically weak compared to other forces. So the main lesson here is that it's lots and lots of tests, and general relativity is passing them with flying colors. So you should be very happy with relativity. This is just showing you a more modern plot. So why do people want to modify things? And so there's several categories of reasons, one of which is a conceptual, or some of them are conceptual, and some of them are more observational. And so I'd like to go through those next. So, oh, you know what? I didn't start my stopwatch. How much time do I still have left?
We started like 15 minutes late, so you have around 45 minutes, 40 minutes.
Okay, I'll set the timer here for 40 minutes. That gives me an idea kind of how I'm doing. I just forgot to turn it on when I start talking. Sorry.
No problem.
Okay. All right. So why do people want to modify gravity? So the quantum mechanics is normally that's the people have known that there's a problem with quantum mechanics for a long time. And there's actually a very simple physical reason why there's an issue with gravity for quantum mechanics. And you think about it, if you're going to test gravity, and the claim is that it's about geometry, then the way you test it is you send out a fleet of people to measure the curvature of space and time to see whether or not it's the motion in that kind of a geometry is what we see when we look at tests of gravity. And to do that, you need a whole bunch of people with very accurate rulers and very accurate clocks who are measuring kind of where events are happening in space-time, and they know kind of their relative positions very accurately, and that's how you would map out the curvature of space-time. And the basic problem with that is going to come from the uncertainty principle because The one thing you ask those observers is that besides being accurate in their measurements, you want them to be also very light because you don't want them to be curving space-time appreciably. You want them to be kind of spectators that kind of go through and measure the curvature of space-time due to other sources. And it's that requirement that you measure accurately and yet also not have much mass, which leads to this problem with quantum mechanics and gravity when you take into account the uncertainty principle. So imagine that you're trying to measure, the curvatures are characterized by a radius. If you think of a line that's bent very sharply, and so it's strongly curved, that is the radius around which, if you imagine inscribing a circle inside there, the radius of the circle is quite short. So curvatures go like 1 over a radius squared typically. And so the measurements of a curvature are like measuring a distance, which is the radius of curvature, and smaller distances are higher curvatures. So imagine that you want to measure some curvature L sub c, some radius of curvature, and so that means your accuracy of measurement has to be less than that if you're going to measure that curvature. So you want the uncertainty delta x to be less than L sub c. What I want to do is I want to take you through to estimate what's the distance, how small does LC have to be in order for there to be a problem with the uncertainty principle. So the uncertainty principle says if you have that measurement of delta x, then I'm putting the h bars back in for once in my life. The uncertainty you'd have in delta momentum is going to be, h bar over delta x, and that's what this is. And if these are relativistic degrees of freedom, then the energy is basically momentum times c, and so that means that the uh, if you have an uncertainty, if you have a likelihood of having a momentum which is could be large, you also have a likelihood of having energy could be large, where I would multiply delta p by c. But gravity doesn't respond to energy, it responds to energy density. So what you need to do is divide by the volume, and we'll imagine that this energy is inside the volume L sub c. And so that means that if delta x is less than L sub c, then the energy density associated with the uncertainty principle is something of the that's at least the size of h bar c over LC to the fourth. And so now the idea is that general relativity tells you how much that gravitates. I'm supposed to multiply that by 8 pi g divided by c to the fourth. And then that'll tell me how much curvature that energy density would give me. And that's what gives me this. But now I have to ask that that curvature is less than the curvature I was trying to measure originally. So that means that L sub c here should be larger than, or the thing I get from g rho over c to the fourth should be larger than the original curvature I was trying to measure. And that leads to this inequality. And if you isolate it for L sub c, then what you find is that L sub c has to be bigger than this thing, a dimensional full thing built out of h bar, Newton's constant, and the speed of light, which is Planck length squared. And so that's basically showing you that there's a floor to how curved the radius of curvature has to be bigger than this floor of the Planck size. If you're going to if you're not going to have troubles in principle with the measurements of the curvature being running afoul of the uncertainty principle. And so, of course, the Planck size is super small. It's 10 to the minus 30 something centimeters. And so it's many, 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 many orders of magnitude smaller than anything we can measure right now. So although this is a problem of principle, it doesn't have to be a problem of practice. And that's kind of the reason even people don't know definitively what the answer is to this problem, but it's an ignorance which is not going to necessarily thwart our ability to predict things in practice in the solar system or on scales where we measure things. Now, that story I gave you was all very nice. It's got a nice physicsy feel to it, and there's lots of twiddles in it. But in practice, what people really have problem with quantum gravity isn't that. They take the point of view. Well, we're not interested in the Planck scale necessarily. I'm interested in quantum things happening on a lower energy. And there's a related problem to the one I just described, which is the obstruction that people in practice hit when they try and calculate things, and that's to do with gravity not being renormalizable. And so imagine taking general relativity and just looking at gravitational waves in it and letting the gravitational waves scatter from one another and estimating what the scattering amplitude would be of a graviton from a graviton or from a classical wave from a classical wave. In either way, you can do that calculation. And if you do that in general relativity, what you do is you imagine taking the metric and you write it as being the background metric, which I'll take in this case to be flat, just for the sake of argument, plus a fluctuation which is small, which is describing the wave. And then you take the Einstein-Hilbert action and you expand it out in powers of the fluctuation. And the thing is, the expansion never stops because the expression for the curvature, you remember, had inverse metrics in it. It had things which are not polynomials in the fluctuation field. But every term in that interaction for the Einstein-Hilbert action had exactly two derivatives. So you get a bunch of interactions like the ones that are written there, where they all involve exactly two derivatives, but there's all possible powers of the fluctuation. And on the dimensional grounds, there's a Planck mass. Planck mass being again the thing with dimensions of mass you build at a Newton's constant, and so it's one over the Planck length essentially in units where h bar and c is one. And so what you do now is you just do perturbation theory like you would have done for quantum electrodynamics, and you can kind of see how the answer is going to go. If you did the Feynman graphs for these interactions that I've written down, every cubic vertex corresponds to a cubic term in the Lagrangian, like the second term in the equation for L in that slide. And that has a coefficient which goes like 1 over m Planck. So the graph on the right, which has two cubic vertices, has to be proportional to 1 over m Planck squared because there's two interactions like per cubic. But you could also scatter gravitons with one quartic interaction, like the last term that's written in the expression for L, and that would be like the graph on the left. And that also it goes like 1 over m Planck squared because in that case that quartic term in the expansion of the Lagrangian has two m Plancks in the denominator. So all of those things give you an amplitude which goes like 1 over m Planck squared, and the dimensions, because the amplitude is dimensionless, come from the energy of the scattering. So I'm going to call that Q. And so you're expecting the answer should look like Q squared, energy squared over m Planck squared, just on very simple dimensional grounds, given that the interactions all had exactly two derivatives in them. And the actual calculation was done in the 60s by Bryce DeWitt, and it's given by that formula 8 pi Ig s cubed over Tu, where St and U are the Mandelstam variables. Basically, they're all proportional to the center of mass energy squared, but T and U depend also on the scattering angle, the angle between the incoming graviton and an outgoing graviton, whereas S is just measuring the energy and has no angular dependence. And because they're all quadratic in energy, you can kind of see that S cubed over Tu is indeed going like energy squared. And G is 1 over m Planck squared. And so the exact calculation is giving something which is very well captured by this dimensional argument. So that sounds all very nice. So people were able to predict what the scattering would look like, and in principle, it's so small you'll never measure it, but it's something which is a prediction. The problem was if you look at the corrections to this prediction, then you run into trouble. So if you imagined looking at more complicated terms in perturbation theory in these same interactions, what happens is that if you have more complicated terms, then you have to sum over all the at higher orders in perturbation theory, you have to sum over the intermediate steps of virtual quantum. It's like in perturbation theory when you're calculating the energy level shifts of an atom. You sum over all the energy levels at second order in perturbation theory, and that same kind of a sum arrives as in the scattering case. And the important thing is that it gives you things that depend on the energy of the scattering that also go like Q. They have more powers of 1 over m Planck because it's higher order in perturbation theory. Every interaction carries a power of 1 over m Planck. And some of the coefficients involve two powers of the actual scattering energy, but they're multiplied by a sum that diverges basically because there's so many states available at high energies, and so you get things that are diverging in the ultraviolet. They're kind of the highest energies in the problem are the integrals are not converging. But a term like in the first line there, which is proportional to q squared, having something diverge there is not such a big deal because you could just say that divergence is something that has the same energy dependence as the original lowest order contribution did. It was going like q squared. So this is maybe I should think of this as a correction to Newton's constant. And I only measure Newton's constant in some physical process, and so I should really only add these together. And I should think of this thing as being something I renormalize into the value of Newton's constant, the same way I do in quantum electrodynamics when I take divergences there and renormalize them into charges or masses of electron when I make predictions without gravity. The problem is that there's also terms like the last line here, which depend differently on momentum or energy than the leading order term did. And so there's things that are going like 4 powers of energy and 6 powers of energy, and they can't be interpreted. You don't have a parameter for them that you can absorb divergences in. And so that's the problem, is it seems like you have divergences like you always do in quantum mechanical systems, but in this particular case, you can't absorb these divergences into the unknown values of various parameters in your problem. And that's kind of what people thought the problem was with calculating in general relativity. So I'm going to put that aside, and that's a solved problem. We now do understand how to do those calculations and why it's possible to handle the divergences, but I'll come back to that. Let me continue the line of thought of, well, why are reasons why people might be unhappy with general relativity that are not to do with quantum mechanics. Some of them are to do with cosmology because we know that we have a great description of cosmology, as you know from the classes you've been taking. But that there's a proviso that it all works very well, provided that you have 95% of what's out there is stuff you don't understand, the dark matter and the dark energy. And that kind of when you first hear that sounds paradoxical that you think you understand something very well, but there's most of what's there you don't understand. And really, the situation is much like it was for atoms 100 years ago. That there people had a good sense that atoms organize what we knew about chemistry and about the interactions of materials way before you could actually see the atoms. And what convinces people about that even if you're not seeing something that is really there is again redundancy of description. If you have to have more than one line of evidence for this thing that you're not understanding. You have to have like 10 or more lines of evidence. And if they all give you the same answer, that gives you confidence that the inference you're making about the existence of these things is reliable. So if you go back to the atom times, there were many ways in which you could estimate the size of an atom and the number of atoms and the mass of an atom by taking macroscopic things like pressures and reaction rates that you could measure macroscopically. And if atoms had nothing to do with what you were seeing, you wouldn't expect different logically independent ways of determining the properties of atoms to give you the same answer if the atoms didn't exist. But they always did, and that was the thing that was convincing, is that you had many ways of inferring the properties of atoms. You always got the same answer, and that gave you confidence that this picture that the atoms were there was actually not a bad picture. Similar story with dark matter and dark energy, especially for dark matter. There's like 10 or more lines of evidence for the existence of dark matter, which I won't describe, but if people ask, I'm happy to talk about. And it's the fact that there are many lines of evidence that gives you confidence that there's something there, even if you don't know what it is. And later on, when we talk about what it might be, the fact that there's many lines of evidence is also what kills many models, is that you have to get all the lines of evidence right, not just any one of them. And so the redundancy of the evidence for these things that we don't see is what's crucial. In particular, dark matter is something where we have lots of evidence for dark matter. And here, these pictures are just showing you of some of the different lines of evidence. The one on the right is a cluster of galaxies, and it's being looked at in multiple ways. This is the famous bullet cluster, and so for example, the you can first of all see the galaxies themselves in this cluster, and by measuring their Doppler the Doppler shift in their light, you can kind of infer how fast they're moving. So you get an idea of what gravitational potential well they're moving in, and that gives you an estimate of the mass in the cluster. The red thing that's superimposed is an ultraviolet picture of the same area, and it actually measures hot gas. And it turns out there's more atoms between the galaxies than there are in the galaxies, and these things are emitting X-rays, uh, and that means they're very hot. And so that means the atoms are moving very quickly. And you can ask, well, what kind of a gravitational potential would I need to trap that many atoms that are that hot into their region? And it gives you a value for the total mass of the cluster, which is similar to what the galaxies themselves do. And so even though the galaxies didn't contain most of the matter, uh, so you might say, well, perhaps the fact there's more atoms between the galaxies might be where why the mass of the cluster that you infer is more than the mass that you see in the galaxies. Turns out that the mass you get in the atoms between the galaxies is still not enough to count for the mass that the cluster has. And the blue thing here is showing you is kind of illustrating that more again, because what they're doing there is they're looking at weak lensing. They're looking at the bending of light as it comes through, and it's distorting the shape of the galaxies in a statistically measurable way. And from that, you can measure the presence of mass in the galaxy, and the blue areas are showing you where the mass is. And the important thing is that all of those three lines of evidence for how much mass there is in the galaxy are agreeing with each other. In this particular case, it's interesting because it's two galaxies, clusters of galaxies that are colliding. And so the distribution of those things they're not all circularly distributed around the center. And so that's also informative. But there's lots of evidence, is what this is really saying, that there is something out there we're not seeing very carefully. And then I just circled, there's this, it's not just, this is not the only evidence. This is not even the best evidence is that that dark matter exists, but there's lots of evidence that it's there. Dark energy is a similar thing. We know that there's two kinds of things we don't know about. We know that they're different because dark matter seems to cluster like ordinary matter does. It's just there's more of it than we see in ordinary matter. Dark energy is something that we also see that the expansion of the universe is accelerating, as you've seen in your classes, and the attractiveness of gravity between ordinary particles and dark matter would never do that. Attractive forces would always slow down the expansion of the universe. So there has to be something else, which is making the expansion of the universe accelerate, and that's the dark energy. And again, we don't know what that is. So because of that, people, it's hard to not. This is just a picture of the one of the lines of evidence for dark energy. In the picture of the galaxy, the galaxy is as bright as that star that you see there, and you might have thought that that star was a star in the foreground, but that's actually not. That star is as far away as the galaxy is, but it's a supernova. The way that people test the expansion rate is they measure the distance to things uh, with a given brightness where they can predict the brightness. And then with the idea being that by comparing the intrinsic brightness that you think it should have to how bright it appears to be in the sky, you can figure out how far away it is. And so by comparing the redshift that you see for the light coming from an object to its distance, which is inferred in this based on the known luminosity of the object, you can map out the acceleration rate of the universe, and that's how they find that it's accelerating. And again, redundancy is important. And so you can see there's a lot of scatter in the errors in the left-hand plot. And the blue oval on the right-hand plot is kind of capturing statistically where you have to be uh, for the errors in the left-hand plot. What's being plotted on the right-hand plot is the total amount of dark matter, which is along the bottom, and the total amount of dark energy, which is the vertical axis, in units which are the units is 10 to the minus 29 grams per cubic centimeter. And that those units are not random units. Those are chosen because we have reason to believe that that's how much stuff there is out there on average. And the reason we know that is that you can test whether the geometry of space at a given time is flat or not. Because you can look at the microwave background and you see a hot area and you see a cold area. You can measure the angle in between those two things. But you also know how far apart they are because that's the distance that that sound waves and hydrogen could travel in the amount of time available to the universe at that time. And you know how far away they are because that's measured by the Hubble scale, which is telling you how fast the universe expands. So now you have a triangle where you know all three sides and an angle. And you remember for Euclidean geometry, you've determined a triangle with two sides and an angle, or three sides. You're not allowed to specify four things separately. And so because of that, you can test whether or not the geometry through which these light rays were passing is Euclidean or not. And we know that it's consistent with Euclidean, it turns out. And so in this picture, the black line, the black diagonal line is when space at a given time would have been flat. And and the agreement of the microwave background measurements of that, they have an uncertainty, which is how far away the surface of last scattering is, and that's the Hubble scale. And so they come in as this orange band here. They can't in themselves tell you that the universe is flat because you have to have some measure of how what the Hubble scale is. Um, but the green band is also a measurement of how much dark matter there is. It's through baryonic acoustic oscillations, but it's basically a measurement of how much dark matter there is. So that's why it's basically vertical on this plot. And they all, you can see, are overlapping in a way which is consistent. And so you could throw any one of those measurements away, and the other two would still tell you that you're living in the place that we think we're living. And where we're living, you can see from the plot, is about close to 70% dark energy and close to 30%, maybe more like 25% dark matter. Um, this is only omega matter here is both ordinary matter and dark matter, so it's about 30%. But of that, only about 5% can be ordinary matter. So the bottom line is that there's, again, redundancy in the inference of the existence of dark energy. And it's inevitable. So what's this got to do with modifying gravity? It's inevitable when you see that is to say think that well, there's two things there that you think are there, and you're inferring their existence from gravity using gravity. Maybe you're getting gravity wrong, and really there's nothing there, but you're just being fooled because you've got the wrong theory of gravity. So everybody tries to have a much more efficient picture where they modify gravity instead of proposing the existence of these two different things. And what makes that fail so far is the redundancy of the evidence. So there's no one picture which seems to do it all. But it's certainly a direction that motivates people to think about that thinking of modifying gravity is kind of it's a very natural thing to do given this kind of evidence we're looking at. There are also conceptual puzzles. You might have heard about black hole information loss, or singularity. The gravitational field goes to an place where the curvatures are infinite at some point, and that means we don't understand what's going on. So there's lots of kind of conceptual things that people also worry about, and And if general relativity gives a crazy answer like infinite curvature, then maybe modifying general relativity won't have that problem. Maybe that's a clue that we should be looking at something different. So that's the other reason which people are usually using when they're modifying gravity. And of course, there's the personal reasons. There's, that if you successfully modify gravity and it turns out to be right, then 100 years from now, they're not celebrating Einstein, they're celebrating you. And so there's certainly a lot of there's a premium on the excitement of finding what the modifications are. And so
So,
there's lots and lots of proposals, and I'm not going to go through any of them in any detail. I'll probably mention MOND again, which is the third one down. MOND is an example where people have tried to describe the rotations of galaxies by modifying not the force of gravity, but they modify Newton's law, F equals ma. They say F is equal to proportional to a different power of a, in order to get the agreement with what people see for the motion of stars, say in a galaxy, to be consistent with what's measured. If you don't do that, then what you find is that the mass you'd need in the galaxy is way more than the mass you see in the stars and in the gas that's in the galaxy. But there's a whole variety of options here. And what I want to later on do is organize them according to what kind of problems they're trying to fix. And that'll be it'll be this group of theories that I'm going to give you a ranking of later on based on the criterion I'm about to describe.
Cliff, would you
Yeah.
like to make a few questions?
Please, yeah, if there's a question, please ask it now because people will never remember afterwards.
Okay, so first question is, which modified gravity models are prominent in weak gravitational lensing contexts? So this is one question from the attendee.
Okay, so I would say that for vanilla weak gravitational lensing, when people use weak lensing to map out the where dark matter is, they're using general relativity. What they do is they say, I know how light bends under if I assume general relativity, and so I know how that should distort the shape of a galaxy, and from that I'm inferring whether or not there's matter there. If you modify gravity, you would have different predictions and you could do the same kind of thing, but you'd have to change what all the predictions were. So there's not a direct connection between any of these theories and weak lensing measurements because the weak lensing measurements are assuming general relativity. I'm not sure if that answers the question, but
Yeah. So there's another question. So it says, slightly off topic question, given that black holes involve extreme curvature, how does the EFT of gravity remain valid around them, especially near the horizon or singularity? What exactly breaks first from the EFT perspective? A very nice
so that
question.
I'll come back to because I'm about to talk about EFTs, and so it'll make the question kind of yeah, people will there other people in the audience will see where the question's coming from. But the short version of the answer is that if you believe the black hole's there, you have to believe that the quantum corrections at the horizon are small because the horizon is what tells you the black hole is there. And the criterion, as you'll see when do the next section, is that the quantum corrections to the horizon, to the physics at the curvature at the horizon, uh, they only start to compete with the classical prediction if the black hole mass is sufficiently small. The smaller the black hole, kind of the shorter the radius of the Schwarzschild radius is, and eventually that Schwarzschild radius becomes the Planck size. And if you ask when is the Schwarzschild radius the Planck size, it turns out it's when the mass of the black hole is the Planck size, which is like 50 micrograms, it turns out. So if you're 50 micrograms or heavier, then the quantum corrections at the horizon are small. 50 micrograms are kind of order one. And so we typically trust black holes, the classical description of black holes, only if the mass is much bigger than 50 micrograms. At the singularity, all bets are off. The curvature is infinite there, and nobody knows what's going on there from an effective theory point of view. So the effective field theory description at the singularity just fails, and we don't know what's happening there. But most of the things we learn about black holes are to do with the horizon, and so the horizon is under control for a sufficiently massive black hole. And certainly, all the ones in astrophysics are they have horizons which are kilometers or the size of the astronomical units across. It's kind of that's the range you're talking about. So they're enormous compared to the Planck size. But I'll say more about that in the rest of the talk. Was there other questions or just the two?
There's one more. So given that the question says, given that the LSST at Rubin data will be coming out, we will have a good volume of data. If forecasting is to be done using them, cross correlated, which modified gravity models would be good candidates for testing?
So that's more or less the point of the rest of the talk is that I think that there's some much better motivated theories than others. And that will be those will be the ones that I think are the ones that are best motivated for testing. So why don't I put that off until the end? And if I don't answer it, re-ask it at the end.
Sure, I'll do that.
Okay. Okay, good. So that those actually set up very nicely the next topic. So there's all these various options. But when I want to talk about, I want to go back to the question of quantum corrections, and that seemed like it was a big, in principle, obstacle to understanding predictions in gravity. And I'd like to kind of recap why that's no longer a worry. That since the 70s, basically, we've understood that how to make predictions in general relativity, including quantum corrections, in a quantifiably where the size of the error is under control as long and it will be under control as long as you're looking at effects on distances that are sufficiently large. Okay, so to set that up, I remind you that the science is a precision thing, and non-gravitational science is the gold standard is things like quantum electrodynamics, where you have things like this example I'm showing you is already actually obsolete because the measurements are better now than when I made this slide. But they already illustrate the point that if you take the anomalous magnetic moment of the muon, the prediction and the first line is the experimental measurement, and then the second line is the theoretical prediction, and you see that they're agreeing to some fantastic accuracy. There's close to 10 decimal places of agreement there, and the brackets in each of the experiment and the theory side are the errors, the estimated errors, and of course the what matters in that comparison is that the agreement is within the errors, both theoretical and observational. And so the fact that the errors are small is part of the story that makes this agreement remarkable. But part of the story in QED, and those corrections that included these higher loop corrections, the quantum corrections that are subdominant in perturbation theory, the fact that you could renormalize divergences into the parameters of the QED was an important part of the story that allowed you to estimate the theoretical error. And so that raises a question for gravity. If you really kind of thought that gravity is classical and matter is quantum mechanical, the problem you have is you don't know what the rules are. And so in particular, when you make a comparison, a detailed comparison like the period decay of the binary pulsar that I showed you earlier on, here's what the numbers were there. It's kind of the agreement. It's not at 10 decimal places, but it's still impressive agreement. It's at the level of a part per million, part per thousand. And but the errors that are there on the theory side are not really the full errors. That error on the theory side, what they really did is they did a classical calculation of what the p dot would have been, and they incorporated the uncertainty they have in the masses of the two partners in the binary, and the only error they're telling you about is the uncertainty propagating the uncertainty of the masses of the two partners in the binary through the classical calculation to get the answer. They haven't answered how big quantum effects are in changing the prediction, which is another source of error. And if you don't have a way to embed classical general relativity in a sensible way in a quantum framework, what you're really saying is you don't have any idea what that theoretical error is, and so then it becomes meaningless to compare to things because you don't really understand when the classical approximation is supposed to work. So we can do much better than that, and that's what this framework I want to describe is about. And so the observation that people made was that the problem in graviton scattering was that you got divergent contributions that depended on energy in a way that was not present at the classical level, at the lowest order scattering level. But you could have had parameters to absorb those divergences if you had imagined having terms in your Lagrangian with more than two derivatives in them. And that's very easy to do. If you imagine that instead of the Einstein-Hilbert action being the action coming down from God, if you imagine it being that there's some action that God gives us, which is a function of curvatures, but we don't know exactly what it is. But all we know is that we're looking at very small curvatures compared to some fundamental scale. Then what you would naturally do is Taylor expand everything in powers of the curvature, and you'd get some series, the first term of which would be the Einstein-Hilbert action. And so that's the point of view that people really take normally when they're doing quantum corrections, is that you're imagining that all these various terms are there. There's, in addition to the first two terms on the right-hand side, which are the Einstein-Hilbert term, including a cosmological constant, you could have also had curvature squared terms, and that could have been, it could have been Ricci scalar squared, it could have been Riemann tensor squared. I'm not writing down everything in this list here. There could be lots of things that are going on there. And everything we know would be consistent with this Lagrangian being the theory of the world. And we're just only looking at it in the limit of very small curvatures because we haven't accessed the high energies that would give us this Lagrangian. And it's even more than that. We know actually where these other terms could come from in a quantum mechanical world. If we have the electron and we look at quantum fluctuations of the electron, we know that those generate terms like the ones I was talking about. When you integrate particles of mass m, you typically get all these various, if you ask how the quantum corrections of ordinary particles depend on the metric of spacetime, they depend on it in a way which would correspond to uh, giving all of these various interactions with specific coefficients. And the mass that's appearing, so for example, there's a curvature cube term where I've written it with the coefficient as being C3 over m squared. I just did that so that C3 was a dimensionless thing. The mass that you would have integrated out is the thing that would appear as the mass on dimensional grounds in front of the curvature cube term. And that kind of gives you a sense as to when you say a derivative expansion, what are you comparing the derivative to? You're comparing it to the masses of the quantum fluctuations, the masses of the particles whose quantum fluctuations would be giving you these changes to the action. That has an important consequence. It means that there's more than one particle we probably don't know about. We have to sum over all the particles we haven't seen at high energies. And that's what the coefficients in this Lagrangian that we would have are coming from that process of summing over all kinds of particles that are being integrated out. And in that kind of a sum, whenever the mass is in the numerator, like in the Einstein-Hilbert term, the biggest one will win. And so it's kind of not a surprise that the biggest scale we know about in fundamental scale is the Planck mass. That's appearing in front of the R term on dimensional grounds. Smaller contributions, smaller masses being added to that won't matter if the masses are small compared to the Planck scale, as all the particles we know about are. But things like the curvature cube term, when we sum inverse powers of mass, it's the lightest one that wins. And so we should expect the thing in front of the curvature cube term would be the lightest. If we've integrated the electron, it should be the electron mass that goes there, not the Planck mass. And so that's kind of it's very plausible that the Lagrangian that we should look at in a quantum mechanical theory is not just the Einstein-Hilbert thing. It's this thing we call GREFT, the general relativity effective field theory, which has all possible derivatives of the curvature. Now you might think that so the people would have said back in the 60s, well, that's all very nice, but now you have an infinite number of parameters. So it's true you can normalize all divergences can go into a parameter, but now the problem is you've got too many parameters, you can't predict anything because you don't have more observables than you have parameters. And that's the mistake that people made. The point is that low energies, you don't need all of these. If you have any fixed accuracy of your prediction you want to make, like 1 part in 1,000 or 1 part in 1,000,000, there's only a fixed number of terms in the derivative expansion you need to keep at any given accuracy, and that only involves a finite number of terms in this Lagrangian. And then once you have a finite number of parameters, as long as you have more observables than that, you get to make predictions, and so that's what people do. And you can quantify that. So imagine now we're going to calculate some process. We're going to take this Lagrangian and we're going to calculate something like in cosmology. We're going to look at correlation functions of fields, or you name it, where anything you want to calculate, we'll calculate it. You can ask, how do these scales like little m and capital M Planck appear in the answer? And the answer is just really relies on dimensional analysis. So if you have a process involving an external energy Q, like we did when we had the graviton scattering, for example, and if you take a Feynman graph involving E external lines, E external gravitons in this case, and L loops, and and V vertices of type N. So I take one of the terms in the expansion of this action involving some number of fields and some number of derivatives, then I can label all those possible interactions and I keep track of how many derivatives they have. That's what dn is, and how many fields come together at that point. And if you just kind of turn the crank and ask kind of how does that answer depend on the parameters in the Lagrangian, you can read it off from the Feynman rules and from dimensional analysis, and this is what the answer is. And this answer is actually, it looks complicated, but it's very informative in many ways. What you should do is, for any physical process, imagine that you fix the number of external lines. So maybe we're looking at graviton scattering, so that there's 4 external lines. The thing that's varying at higher orders in perturbation theory is the number of loops and the number of vertices in more and more complicated graphs. So what we want to ask is, what's the biggest contribution to any one process as you make the graphs more and more complicated? And what you see is that every time you add a loop, it costs you a factor of the energy divided by 4 pi m Planck. And basically, the classical approximation is the L equals zero limit of these graphs. And that's telling you why the classical approximation works. The classical approximation, what justifies the classical approximation, is the low energy limit. The corrections in pairs of derivatives is also the thing that they all come with an H bar. And so the thing that suppresses quantum corrections is the same thing that controls the low energy limit. And so if you ever find that your derivative expansion is bad, one of the worries you should have is that the semi-classical approximation is also bad. You get suppression here anytime you have an interaction involving more than two derivatives. That's what this factor has. Then you pay the additional price on top of the number of loops of 1 over energies divided by these other scales to some power. And the more interactions you use, the worse it is, the more suppressed it is. Things involving zero derivatives, like the cosmological constant or the scalar potential in a scalar field theory, they actually are the only things that have a Q in the denominator. They tend to undermine the ability to do the low energy approximation. And so you have to be careful about those ones. But that's a different story. The bottom line is that there's a very crisp statement about how big the corrections are due to quantum mechanics. And if you, for example, looked at the black hole case that someone asked about, then in the black hole case, the scale at low energies would be the energy Q would be 1 over the Schwarzschild radius. So there was a Hawking temperature, another way of thinking of that. And so if you ask what's the size of the quantum corrections, they're being controlled by, in that case, the Hawking temperature divided by 4 pi m Planck. And and that gives you that tells you how big the quantum corrections are. So that you can see from that that if the Hawking temperature had been at m Planck, which is another way of saying that the radius of the black hole is at the Planck length, then these corrections would be order one, and you wouldn't trust any classical properties of the black hole. But for physical black holes where the radius is bigger than the Planck scale, then the things are under good control at the horizon of a black hole. But so you can apply essentially these estimates in any particular case that you're trying to study, and you can quantify how big the corrections are. And in the solar system, if you're not doing a black hole, you're doing corrections in the solar system to the Cassini probe. They turn out to be 1 part in 10 to the 80, so they're extremely small because the scales involved in the experiments are so large compared to the Planck length, essentially. It turns out there's a lot of benefits to this kind of a picture, which is explored by Weinberg, and we now understand in this framework why general relativity, if you have anything that's grabbing gravity at all, at low energies, it has to start looking like general relativity because whatever your full Lagrangian was as a function of curvature, it at low energies is always looking like the thing linear in curvature, and that's what general relativity is. So as long as you have only the metric, at low energies, almost anything you do at high energies is going to look like general relativity at low energies. And that's a very powerful picture. It shows you that you might have a lot of things you could be doing at high energies that could change physics, but they're all going to hide themselves from you at low energies. That's why it's hard to test quantum gravity at low energies. The same thing happens for Maxwell's equations. The most general way you can couple a massless spin one particle basically is Maxwell's equations. So we have a very robust picture as to why electromagnetism works. We're not really thinking that Maxwell's equations are going to, there's a factor of two wrong in one of the terms. There's really very general arguments that tell us that it's what you have to see. And the standard model has a similar property that it's the most general thing you can have at low energies given the particles and the symmetries of the standard model. So there's an inevitability to some of the theories that we have in fundamental physics that kind of follow from this effective description. So I'm going to kind of, I see that I'm very close to the end of the time, so I'm going to kind of just very quickly go through the punchline of, so what does that story I just told you tell you about how you organize things with different modified gravity? So we had all these different kind of motivations for modifying general relativity. There's consistency with quantum mechanics, and there was the existence of dark matter and dark energy. There were conceptual puzzles, and there was flame and glory. And so in this effective description thing, what you should do is organize them according to, are they affecting things at low energies or are they affecting things at high energies? At high energies, there's lots of things that could happen and we wouldn't know much about it at low energies, but at low energies, that's where we're doing all our measurements. That's harder to hide. So the consistency of quantum mechanics story, that was, remember, a short distance problem. That's something which is really a pressing problem at the Planck's length, but not really so pressing at higher length scales. The dark matter, dark energy, and the conceptual things, they tend to be long distance things, particularly the ones from cosmology. Cosmology is the longest distance that we know about. And so the physics of that is in the very much the long distance world. So the things that are being modifications to gravity that are motivated by, say, getting rid of dark energy, they're much harder to make work in this derivative expansion language. It doesn't mean that that's not the way nature works, but it means that if you think that you are going to not have this derivative expansion language, you need to have a way of quantifying what your theoretical errors are. And the only, to my knowledge, concrete way of quantifying that so far is in this derivative expansion language. The fame and glory thing, that's not a long or short distance problem. It's a personal problem, but it's so now take these theories that I kind of listed. I gave you a list of theories. I didn't tell you what they were, but you can also organize them about whether or not they were motivated by a long distance or a short distance problem. And so these ones, the F of R theories and the many of the massive gravity theories, they're aimed specifically at the dark energy. So they're motivated by changing physics at long distances, not at short distances. There's a variety of theories where they break Lorentz invariance, for example, or you have a variety of fields, and they actually have a bit of a both long and short distance motivation. Some of them are kind of motivated partly by string theory, some of them are motivated by, but it's also true that things like Lorentz breaking are things that it's difficult to hide short distance breaking of Lorentz invariance from long distance physics. So there's kind of a aspects of both long and short distance motivation in those theories. Things like string theory and many of the traditional quantum gravity theories, they are specifically motivated by this Planck problem of the quantum fluctuations at very small distances. And so they have a very small short distance motivations. So, so what does that tell us? One of the nice things is that amongst that last class, there are examples of theories which do make sensible quantum predictions for gravity at arbitrarily high energies. The one that's best developed is string theory, but that's kind of remarkable we have any theories. Even if string theory isn't what nature does, we never before had the theory which could be something which describes quantum effects in gravity at very high energies. And now we do, and so that gives us we now can ask questions about, so it's at least some questions about what's going on at very high energies in a quantum mechanical way. Now, one of the things that you fight is this general statement that in the derivative expansion, all you measure is at low energies. And no matter what you thought was going on at high energies, whatever you thought your Lagrangian was as a function of curvature, at low energies, you're only measuring the first few terms in that Taylor expansion, and that always looks like general relativity. So the fact that string theory reproduces Einstein's equations is not really regarded as a big success. Any theory at all at high energies that has the right particle content will give you general relativity at low energies of very general reasons. And that's not just a string theory problem. That's true for all of these small distance modifications of gravity. That there's a property of nature called decoupling that short distance physics generally is not important when describing long distance physics. That's kind of why we could describe atoms without understanding nuclei. And that's great if you're trying to understand why your low energy predictions are robust, given your ignorance about high energy physics. But if you think you understand the high energy physics, like the string theorists do, it becomes a problem because very few things depend on those details if you're at very low energies. It doesn't mean they're stupid. It just means that they're fighting this property of short distances decoupling. So there are theories that make sense, and it's true that they typically agree with general relativity at low energies as they must. But if you have a theory which is not in this category that is described by derivative expansion, so for example, F of R theory, sometimes people write this curvature action as not being a series in powers of curvature. They write it as being one over curvature. So something which is very singular for small curvatures. That's something where what's missing is an argument. What people normally do is they just do classical calculations with that action and they don't ask how big the quantum corrections are. But what's missing is there has to be some quantification of what the corrections are, the quantum corrections are. And if you don't have a derivative expansion working for you, you have to figure out what the small quantity is that justifies the classical approximation. And that's often not done, but I think that's not good enough. I think you have to really, the bar is to compete with all the other proposals, you need to have some sort of understanding as to what your theoretical error is quantum mechanically. So if I take the ones that I showed you and I kind of ask, how are they doing? I put F of R theories as being red because I'm thinking there of the 1 over R as opposed to R plus R squared plus curvatures. Things that involve some generic number of small spin fields like scalars and vectors and tensors, those are the ones that are the least objectionable. They're the ones that arise in known examples like string theory. I kind of have a shading between yellow and green there because I'm going to show you in the next slide that there's a subdivision of them as to which are more plausible. These ones that are yellow are ones where I would say that it's not clear that there's a controlled approximation there, but it's also there's no no-go theorem. And so I think people who do those theories it would be useful if they were if they could actually make the case as to what controls the errors in their predictions. But there may be a good argument. It's just that it hasn't been made. Of the theories that it just involve some slow spin fields, there's a subclass where the properties that you're using at low energies are kind of very generic for a theory, and there's another subclass where they're not. And the ones where things are very generic, those are the ones that for which there's the rating would be green. Those are the safest ones. What's interesting about cosmology is that the things that cosmology likes, like small vacuum energies and small scalar masses, so that things can roll around interestingly at late times, those are things that are not generic at late energies, at low energies, and so they want to be in this yellow category. And the trick is, the clue there is to find the reasons why the properties that you're using are really more generic than they would have otherwise have been. If you specifically are motivated by dark energy and dark matter, but that's the reason why you're inventing a modification to gravity. I would say that the safest statement now is that there's just no known example which gets it all right. You can get specific things right. You can modify gravity and understand rotation curves of galaxies, but those same theories then don't give a good description of clusters of galaxies or cosmology. So to my knowledge, there's no one theory that just gets the evidence right for all of the lines of evidence for dark matter, for example. Whereas if you're a particle physics graduate student, you make a dark matter model every Tuesday because it's super easy to do. And when you do it, you get all of the lines of evidence right at the same time. All you need is something which has a mass which is not so different from the particles we know about, and which has interactions which are not so different from the particles we know about. And you just have to make it stable so that it doesn't decay. And then that likes to be the dark matter. And so there's lots of ways in which you can account for all of the lines of evidence by adding new ingredients to the universe, but with regular gravity. And so, even though that may not be the way nature works, I think right now, if you ask what's the preponderance of evidence, the preponderance of evidence is that a new species of matter is more likely to be what's going on for dark matter than any modifications of gravity, just for the absence of, for not for want of trying, but no one's been able to find an example of modified gravity that does it all. There's also no evidence for what I would call gravitational exceptionalism, that gravity is so different from all the other kinds of physics that sometimes you run into in the relativity community. So the upshot is that it's hard to modify things at long distances. It's fairly easy to modify things at short distances, but when you do that, that often has very little effect at long distances where we do the measurements. And that's a good thing if we don't want our predictions to care much about the details at short distances, but it's a bad thing if you're trying to figure out what the right theory of the world is at short distances. The effective field theory derivative expansion story, I think, is one of those take to the bank stories that it's crazy not to use. It tells you what the theoretical errors are in predictions in a way which is very robust, and it applies in other areas of physics too, not just in gravity. It doesn't mean it's right, but if it's not right, we need a replacement for it, and that's the thing that is often not presented. So I think the lesson is that there is a way to sort amongst these various proposals, and some of them are better motivated than others. And typically, the ones at short distances are the ones that are modifying things at short distances are the ones that are best motivated. But it's also true that those are also the ones that change things, at the very least, in the observations. And so the sweet spot where you kind of both modify things at short distances and there's things that are happening at long distances is a much more difficult thing to do. And that's the opportunity, is that the fact that it's not easy to do is the thing that observations in cosmology by themselves will probably not tell us what dark energy is, for example. But it's the subset which makes sense as a low energy limit of what we know about nature that also agrees with observations. That might be restrained enough that we could figure out what's going on just with that information. So that's my prejudice. Thank you for listening. And I hope you enjoy the rest of the school.
So thank you so much, Cliff. And maybe we can stop the recording and get to the questions.